right? So in the last class, we discussed about uniform plane waves, and today we are going to continue discussing about uniform plane waves. Apart from that, we are going to discuss about the characteristics of uniform plane waves. After that, we are going to discuss about the transmission lines, some concepts regarding transmission lines, and then if there's some time left, we are going to discuss about the antenna systems, specifically about dipole antennas. So these two sections, I will give a brief summary about their functions. So I'm going to continue about the continue the section regarding this uniform plane waves in the first half, in the first section. So right, so we were doing some mathematical derivations regarding uniform plane waves. So I will give another like a small introduction to uniform plane waves in case you cannot remember the where these uniform plane waves are getting generated, and why we are going to analyze them. So I will briefly draw the place or the situation where we observe uniform plane waves. So if we have a certain source, of current, for example, so with a source with varying current, a source that produces varying current can generate varying magnetic fields around it. So we can observe like magnetic fields generated around this varying current. So if we take, for example, an antenna, in an antenna, we are supplying a varying current to the antenna feed point. And once we change the current up and down, then the magnetic field is created around it, and antenna radiation happens around the antenna. So using the radiation, we can transmit energy from our antenna to another location, to a long distance. So we want to generate high high energy around this antenna, and therefore we design the antenna such that the radiation is very high around the antenna, and then it will propagate in the space towards another antenna. So since the source is at this location, the energy of the antenna around this location is propagating and in a spherical nature around the source. So the radiation energy that we can observe around the source location, is of spherical nature. So we can observe radiation in a spherical manner around the source. So if we move a little bit further along the antenna, along the z-axis, let's say this is the z-axis. If we move further along this z-axis and very far, I mean considerably far from the source, then we say that we are in the far field, right? When we are in the far field, we call that we are very far, considerably far from the source of the varying current. So when we are in this location, we still can observe radiation. The radiation will still be in a spherical manner around the antenna. However, the radiation that we observe at a certain location like this will be can be mapped onto a flat plane. The radiation that we can observe at this location can be mapped onto a flat plane. So in this flat plane, the electric field and magnetic field that are created are along these directions. For example, the electric field will be along the Z x-axis, and the magnetic field will be in the y-axis. So if we take magnetic field coming out of the board, then we will say that since we take Z-axis along this axis, we will take that the magnetic field will be along the perpendicular direction to EX and Z, and then it is like coming out of the board towards us in this direction. So the magnetic field and the electric field that are generated in this plane will be perpendicular to each other. So the wave that is getting propagated at this location is known as the uniform plane wave. So the uniform plane waves are generated at a far field location from the source. So so once the radiation has decreased up to a certain considerable amount, and it has come to a level that it is propagating in a considerably constant level at this point, then the plane wave that is generated also has a constant amplitude, and it will travel with a constant amplitude and constant frequency. So we are going to analyze this plane wave, which is having those characteristics. So the plane waves have constant amplitude, constant frequency, and they will have a certain velocity of propagation, and they will have some other parameters. So we will discuss about those parameters in this section. So in the last class, we discussed about the situation where we derived the electric field of the uniform plane wave, right? So in the last class, we have we took the wave equation, which is given by this equation, right? So this is the wave equation of the electric field. So the wave equation is showing us that the electric field is behaving or propagating as a wave in the plane, right? So the magnitude of the electric field is varying as a wave while it is propagating along the Z axis, right? So now we consider that the electric field is only changing along the Z coordinates, and it is changing with respect to Z coordinates and time. So let's consider the X component of the electric field, and we will study the behavior of that electric field component and its behavior using this wave equation. Okay, so we are going to only take the x component of the electric field, which we call as the Ex. So x component of the electric field we take right. So we take that component only for the moment, right? So there could be other component which is along the y-axis, right? We will take that also into consideration later, but for the moment, let's consider the x component of the electric field, and we are going to take the assumption that the component of electric field is only varying as according to z coordinates and the time coordinates. They do not, the electric field component Ex do not vary along x or y directions. That means the value of the electric field do not vary along the x coordinate axis or in the y coordinate axis. So what I mean is that once a wave is propagating up to this point in the space, right, there's a plane over here. So once we study the plane, the electric field and the magnetic fields around here, the fields that are generated here do not vary along the x-axis or the y-axis. That means their magnitude, the amplitude do not change along the x-axis or the y-axis. So if their energy is increasing over the time, that means it is something like not usual. So if the electric field amplitude is increasing over time, that means that another energy source must be provided for it to happen like that. So in order to conserve the energy, the electric field and the magnetic field do not vary along the x and y directions, right? Apart from that, the electric and magnetic field also do not increase or increase its energy along the z axis. It does not increase its like amplitude along the z axis. It might decrease its amplitude due to the attenuation that might occur in the that might occur due to the obstacles or interferences from the environment, from the medium where it propagates. Right. So the amplitude can decrease, but the amplitude cannot increase even in the z direction. So the electric field Ex component is only like function of the z axis and the time axis because it is propagating along in that direction. So because of that, we need to use these z parameter and the time parameter to define where exactly this electric field is getting generated at a certain instance of time, right? So in the z-axis, we can define like at which location the electric field is generated at a certain time, right? What is the z value? It could be a certain value, right? And at what time it is getting generated. So at z1, z1 t1, the electric field could be having certain magnitude. At z2 t2, the electric field could be having a lesser amplitude, and it might have a wave-like front, right? So the electric field will behave like a wave along the z-axis, and it will continue to have the same amplitude. It will have the same amplitude, have the same frequency as it propagates along the z-axis, right? So it will have the same amplitude. Amplitude won't change. Amplitude means the maximum displacement that the electric field can take with respect to the zero axis, right? With respect to the reference axis. So the electric field will behave like a wave. So its magnitude will change like this. It will have a wave like amplitude variation, and it will have a maximum amplitude, I mean maximum displacement. Then displacement will decrease. It will reach zero. It will change its direction. It will have a electric field generation in the opposite direction will reach a maximum over there in the opposite direction as well, and then again it will decrease, and then it will reach a zero, and then again the same pattern will continue. So this is the wave-like behavior of the electric field, right? So the wave-like behavior of the electric field will be like this. Okay, so these things we are going to mathematically denote, right? So so in the last class we denoted this equation, wave equation, and we also mentioned the solution for this equation. Okay, so the solution for the equation A will be of the form. If you have any questions, you can ask. Right, so we have the solution in this form. Okay, so I will explain to you what K is. So omega is the angular frequency. Z is the displacement along the Z axis. Okay, so K is actually something I will explain later, but for the moment you can remember it as the wave number. This is the wave number. It shows us the rate of the change of phase of the wave. So the rate of change of the phase of the in the wave, right? So I will explain that in the next sections, the rate at which the phase changes. Okay, so I will explain that. Okay, so this is what we have discussed in the last class. So this is the solution of the general solution of the equation A. Okay, so this solution can be understood as the addition of the forward wave and the backward wave. Okay, as the addition of the forward wave and the backward wave. Right, so this is the backward wave, this is the forward wave. So I will erase the these top sections. Right, so in this in this study we are only going to concentrate about the forward going wave. Okay, so the thing is, now forward wave is something we are going to consider when we consider our radiation or our antenna propagation, our wave that is getting propagated from a certain antenna along a certain direction. We are only going to consider the forward wave. The reason is the backward wave only or most of the time occurs when it hits a certain object and it reflects back, right? So only if the wave is going in another direction, which is opposite to the direction of the initial wave propagation. So if the wave is going and hitting a certain object in the space, then there's a backward wave that is getting generated. So only in that case we might need to consider the backward wave. We will consider about this backward wave in the transmission line section. So until then, we will only consider the forward wave. So we will consider only the forward wave to analyze the uniform plane wave that is occurring in this location. Okay. If you have any questions, you can ask. I will answer them. We will assume, we will consider only the forward going wave component. Okay, we will consider only the forward going wave component for the moment. Okay. Therefore, the forward going component is actually this component, right? This component we can denote in other ways, right? So we can denote this using phasor domain, right? So using phasor notations, we can denote this as the real part of the phasor representation of this component, which can be represented like Ex plus e to the plus j omega minus kz. Okay. So plus j omega t minus j kz, right? So right, so if we take this, if we want to simplify, we can denote this as e to the plus j and inside brackets omega t minus kz, right? So by taking the real part of this phasor domain representation, we can get this expression, right? I hope it is clear to you. So if we take it like that, we can also do some easy calculations by using the phasor domain representation of this component. So we will keep it like that for the moment, right? We will keep it like that for the moment, and I also want to yeah, so we will keep that result as like that, and then we will go into the next we will go ahead with the next title, where we discuss about the properties of the uniform plane wave. Okay, so when I'm discussing that, I will go back to this equation that I represent uh, the Ex component as a phasor domain representation. Okay, so we will first discuss about the properties of the uniform plane wave. So first property is that the component of electric field along the x-axis is zero, right? So the component of Ex, right, along the z-axis is zero. So what I mean is that once we have the uniform plane wave, right? Now the plane wave is having electric fields in the x direction and the magnetic fields in the y direction, right? So we have the magnetic fields in the y direction. So magnetic field I can write as Hy, and the electric field I can write as Ex along the x direction. Let's say this is the x direction, this is the y direction. So this axis is the z axis direction. So if this is the case, the component of the EX, right? The electric field component along the Z axis is 0. The wave is propagating along the Z axis, but the projection or any components of electric field along Z axis is 0. There are no components along the Z axis, right? Only we have the components of we do not have any components of either the electric field or the magnetic field along the Z axis. So the components of the EX electric field along the Z axis is 0. Also, the component of the magnetic field is also will be 0 along the Z axis. So, right. So this is happening in uniform plane waves. So in the uniform plane waves, the electric and magnetic fields only lie on the plane. They will only be lying on the XY planes, right? So the components of electric and magnetic fields will only lie on the plane, right? Only lie on the XY plane. Okay, so that is the first property of the uniform plane waves, right? So we will discuss about situations where this might not happen in the real applications, where the components of electric field and the magnetic fields are in the direction of the wave propagation as well. However, in the uniform plane waves, the electric and magnetic fields are only on the XY plane, right? So this is the XY plane, right? This is the XY plane. The electric and magnetic field components are only in this XY plane. It's a very simple idea. No components of electric and magnetic fields will be along the Z axis. The Z axis is the axis along which the wave is propagating. Okay, so that is the first property. Second property is that we have the electric field and the magnetic fields always perpendicular to each other, right? So that is the second property. I'm going to erase these diagrams. So I want you to keep this diagram in your head in order for you to understand easily what exactly at what location we are analyzing this wave that is getting generated from a source like antenna, for example. Okay, so this is like antenna. So the antenna is a equipment that creates radiation using varying current. So the varying current produces varying magnetic field. Those varying magnetic fields create varying electric fields, and so on. Energy is getting generated because of the generation of the magnetic fields and the electric fields, and due to their amplitudes, energy is getting generated. So at the location where the antenna is, we have high radiation, that means high energy. And then once we move further and further away from the antenna, the radiation energy of the antenna decreases, and the amplitude of the electric field also decreases, and magnetic field and electric and magnetic fields also decreases, and therefore the net the amplitude of the wave will decrease up to a certain level. However, like once it reaches a far field destination where where we have like a plane like wave front, then we have the electric field and magnetic field lying on a uniform plane wave, right? Apart from that, the amplitude of the electric and magnetic fields will be uniform or will be equal in that region where the wave is propagating. The first reason for the amplitude to be equal is that we consider a lossless medium. right? So we consider a lossless medium. So in the lossless medium, we do not have amplitude reductions, right? So amplitude will be same along the direction of propagation because the medium does not attenuate the wave amplitude, right? So the medium that we consider here is a lossless medium. So the wave will propagate with a uniform amplitude along this environment. Okay, so that kind of a wave only we are analyzing currently. Okay, so the second property that we are studying about this wave is the direction of the electric field and the magnetic fields. Okay, so the direction of the electric field and the magnetic field will be perpendicular to each other in this type of waves. So I will write it. Right, so the direction of the electric field and the magnetic field will be perpendicular to each other. That is the second property. Okay, so how can we mathematically prove that? So we can mathematically prove that. I will quickly do that. Okay, so using Maxwell's laws, we can take the Faraday's law, and then we can write that this is the Faraday's laws equation. We can simplify this further, but for that I need some help from this equation that I have derived earlier. So I will say that this is capital A. So once I take capital A, I need to simplify it in a certain manner such that I can take some output for a certain expression. Okay, so I will do it. So I'm going to differentiate the equation A with respect to time. Okay, so once I do it, I will be able to get some important result, right? So differentiate the equation A with respect to time. So once I differentiate with respect to time, the differentiation is very easy once I use the phasor domain representation. So I'm going to take the phasor domain representation and I'm going to take the differentiation with respect to time. So once I do that, I will be able to show that the differentiation with respect to time of this expression will be equal to an expression where I take now in this expression, as you can see, the time variable is only available in this omega t term. So therefore, only j omega will come out of this expression. And then I will be left alone with the rest of the expression which was earlier there. So there's no other changes to the initial expression where we have ex plus j omega t minus kz. So the same expression that we had initially is left, only the difference is j omega term came out. So once I compare this with the left-hand side of the equation, right? So the left-hand side of the equation, I can say that d over dt is equal to j omega. Okay, so d over dt is equal to j omega. I will write. So this is d over dt is equal to j omega. So this is the result I wanted to take, right? So whenever I see that there's some differentiation with respect to time, I can take j omega instead of it. So once I substitute j omega, every place where I see a d over dt or a differentiation with respect to time, then I can apply it in those locations. Okay, so right, so in here actually I'm not taking the differentiation, I'm taking partial differentiation because we are working with two parameters. Okay, so partial differentiation should be taken here, so I'm taking partial differentiation on both sides. Okay, so in here dabba over dabba t value will be equal to j omega. Okay, so this is something that we might need to keep in our mind. So this is an important result. Apart from that, we can also differentiate the equation capital A with respect to Z, right? So once I differentiate the capital A equation with respect to Z, I will get another result saying dabba over dabba Z is equal to minus JK. Okay, because the minus sign is there in front of K. So because of that, we have minus JK as the result of dabba over dabba Z. So we have these two results, and we need to use these results in our equations. So we will be able to make our derivations easy with these results. So with those results, I will now simplify the equation that I wrote earlier, which through which we are trying to find the direction of the electric and magnetic fields, and we are trying to get the result that they are perpendicular to each other. Okay, so I mean we will get it mathematically using these equations. So if so first of all, I'm going to substitute the dabba over dabba t with j omega, and then I'm going to rewrite this. So minus j omega, and then b I'm going to replace with mu h, right? So mu h I will put instead of b. You know, b is equal to mu h, so I will replace like that. So this is the equation that I'm getting, right? So if I want to find the direction of the magnetic fields, right? So if the direction of the electric field is x, now since we are taking in all our examples, we are taking that direction of electric field is along the x. So if it is along the x direction, what is the direction of h? So that is what we are trying to find. So we will take the magnetic field as a subject of this equation, and then I will write the rest of it on the other side of the equation. So I will take that the direction of the x electric field is along the x-axis, and then I will write that electric field is varying with z and t, and then I'm going to divide by j omega mu, and then minus sign is also here, right? So once I once I take the curl of the electric field, that is also something mathematical. So so you need to expand the electric field function using the determinant of the i mean I mean ex. Okay, so the curl operation you need to do here, right? So this is the curl operation acting on ex component. Okay, so curl operation acting on ex component, you can write as the determinant, right? The determinant of the ex with the curl operation. So I'm going to write the curl operation like this, right? Where I define that the internal elements will be like this. So the curl function is defined by definition like this. So these are the things that we discussed in the very initial sections of electromagnetism. So in those lectures we discussed these things. So the curl function of the curl function of the ex component can be written using the determinant like this. So right, once I solve this, I can write the solution as the solution as I will write it in here. Dabba over dabba, I said actually there's not enough space. Minus dabba over dabba, I said. Ex is a t y hat over j mu omega, j omega mu. Okay. So after that, you can actually substitute the result that we obtained earlier, which is W over W Z is equal to J minus JK, right? So I can substitute minus JK in here, and then minus JK, and this minus will cancel out. So only JK will remain, and I will be left with EX is a T Y hat and over J omega mu, J omega mu. Okay. So this is what we are left with. So once so this is, yeah. So the answer, yeah, this numerator part I got as the answer for this curl function that I mentioned earlier. And then I substitute the denominator of j omega mu to obtain the value of h, right? So this is the equation for the h. So from this equation, we can see that we can actually cancel out the effect of j by cancelling the effect of j on both numerator and denominator. And then we can see clearly that the direction of h is along the y direction, y-axis direction. So if the direction of electric field is along the x-axis, the direction of the the magnetic field is along the y-axis. So the direction of the magnetic field is along the y-axis. So if we have the EX component or the electric field component in the x direction, the magnetic field, corresponding magnetic field component is occurring in the y direction. So if we have other complex scenarios, this concept will remain the same. So for example, in the simplest case, you can assume that the total electric field is along only in the x direction. If that is the case, the total magnetic field will be along the y direction, right? So so with this, we can prove that the magnetic and the electric fields are perpendicular to each other. So that is the output of this this derivation. So the electric field and the magnetic fields are perpendicular to each other, right? So we can also now in this case we have considered the case where we have EX or the component of electric field in the x direction, right? And we have considered only the component of the electric field only in the x direction. However, we can do the same thing for the case where we have the component of E along the y direction. So if we have the component of electric field along the y direction, then we can show that a corresponding magnetic field component is along the x-axis. So by the combination of the electric field and the magnetic field components like that, we can form the resultant electric field direction, and we can show that the resultant magnetic field direction is perpendicular to that. Okay, so finally, what is the conclusion is that the total electric field direction is perpendicular to the total magnetic field direction. I hope it's okay with you. If you have any questions, you can ask. I will move to the next property, and I will explain that property, and I think we have about 2 more properties. So I will write the results we have obtained earlier with regard to W over W T equaling j omega which is the important result, and above Z equal to minus J Z, sorry, JK. So So the third property is the wave impedance of the uniform plane wave. Okay, so the wave impedance of the plane wave we can define using the electric field and the magnetic field. So, so the wave impedance is given by the ratio of electric field and the magnetic fields. So in the previous, property, we discussed that the component of, for example, the magnetic field is equal to the JK EX, which is also a vector that you can denote the vector component using an arrow on top. And then we derived this equation like this in the previous previous section now, just recently. So we got this expression. So if we take the ratio between EX and the HY, that means the components of electric field and magnetic fields, we can obtain an expression where we can show that it is the impedance. It is an impedance value, and this impedance value is actually denoting the impedance that the medium has to the wave propagation. Okay, so in here now I have taken the ratio between the electric field and the magnetic field, and that ratio I can denote by the omega mu over K. Okay, so we know from our previous lessons that the electric field has the units of volts per meter, and the magnetic field has the units of amperes per meter. So once we take the ratio between volts per amperes, we have the units of omega, right? Resistance. So we have the units of resistance as the final unit. So therefore, the ratio of electric to magnetic fields components gives us a resistance value. So if we take the total electric field is along the x-axis and the total magnetic field is along the y-axis, then we can denote the ratio between the electric field of the wave and the magnetic field of the wave like this. So then that can be represented as omega mu over K, right? So K is, as I told you before, it is a wave number. Okay, so what is the wave number? Now that is something we want to discuss, right? So wave number is something that we can define as the amount of phase change per unit time. Okay, so this parameter is giving us the rate at which the phase is changing in the wave. So this number, this value of K is also defined as in different manners. Actually, it is defined. So the value of K can be defined using the equation W square root mu E. Okay, so this is an equation that we can use to find the value of wave of K, right? Find the value of wave number. So how did we get this equation, right? So that is the next question. So in order to do that, in order to show how we got that, we need to solve the wave equation in a different manner using the results we have, the results that we have taken in here. Okay, so the results that we have taken in here, we can derive we can derive an equation from the wave equation, starting from the wave equation, another equation that shows us the wave number or the presence of the wave number and its equation. Okay, so we will start to just prove the equation of the wave number. I mean, proving means like we are defining the wave number. We are defining the wave number parameter in that equation, right? So this derivation is known as the Helmholtz equation derivation. So starting, we are going to start deriving that. So deriving the Helmholtz equation. Helmholtz equation. So the Helmholtz equations were derived by a German scientist. So this equation is used to actually understand the wave equation and simplify it further. So the wave equation we use is this equation where we have the Laplacian of the EX, I mean electric field component, which is equal to the mu E of mu E and the second derivation of the electric field with respect to time. So we have the result of W/W as j omega. So we use that to simplify this equation by substituting j omega in place of W/W. So since this second derivation, we are going to take the second order or second power of j omega, and then we are going to take the multiplication with this component. So with this, now we have a very simple equation where we can take the components of EX onto one side, right? So we can take this Laplacian operation plus, right? Because in here we have j omega squared, which means minus j omega squared, right? So which means minus omega squared. So that means once we take it to the left side, we will take plus omega squared, then mu E epsilon. Then we can take EX ZT, right? So this equation where we denote the electric field, right? Electric field in this manner is known as the Helmholtz equation. Okay, Helmholtz equation is this. We can generate a similar equation for the magnetic field also, right? We can write a similar equation for the magnetic field also, right? That is where we replace this EX with HY. Okay, so we can write similar equation for the magnetic field also, because magnetic field also follows this wave equation, and we can substitute j omega for that equation as well. Therefore, we are left with this type of output as the Helmholtz equation related to the magnetic field. right? So Helmholtz equation related to the magnetic field. So this is what we can obtain, right? So I'm going to erase the magnetic field components and its Helmholtz equation. I'm only going to consider the one related to this electric field, right? So in this electric field based Helmholtz equation, we can see that this term is omega squared mu epsilon, right? So this is the component that we define as the wave number. So this component we define as k squared actually. So the value of k will be equal to omega square root of mu epsilon. So this is what we define as the wave number. So the wave number was defined in this equation. So that is how we got the wave number equation. So the wave number is important for us to define the intrinsic impedance of the wave, right? So the wave impedance. Okay. So we were talking about the wave impedance earlier. So I will continue regarding that. Okay. So this wave impedance we also call as intrinsic impedance, right? So the intrinsic impedance of the wave. So I'm going to erase this. So in order for me to find the intrinsic impedance in its most simplest form, then I need to substitute the value of k in terms of omega and mu mu epsilon, right? So then that I will be doing in here. So I'm going to substitute omega mu over omega square root mu epsilon e. So epsilon, and then the ratio between the electric field and magnetic field, I'm going to denote using the parameter eta, right? So this is known as eta, right? So I'm going to use the eta symbol to denote the intrinsic impedance. Okay, so I can simplify it further and I can obtain this expression as the intrinsic impedance of the wave, right? So this value we can obtain for the free space using the free space mu naught and epsilon naught. So for the free space, I will denote the eta as eta naught, and mu naught over epsilon naught will give me the intrinsic impedance, right? So since I know the values of the mu naught and epsilon naught, I can substitute them inside this equation, right? 4 pi into 10 to the minus 7 and divide by 8.854 into 10 to the minus 12, right? These two values we can find and we can substitute. These two values can also be defined using phi, right? 4 phi into 10 to the minus 7 divided by 1 over 36 phi into 10 to the minus 9, right? So why did I do like this, right? So the reason is now we have the top and the bottom values of mu naught and epsilon naught in terms of phi. Once I have the values in terms of phi, I can get the output in terms of phi as well. So the output value of the eta naught for the free space will be 125 in terms of the phi, right? So this is the value we can take. Apart from that, we can take its actual value by substituting the value of phi as 377 ohms. 377 ohms. Right, so the value of the impedance that the medium has on the wave propagation when the medium is a free space is 377 ohms. So there's a resistance from the medium of about this range to the wave propagation. But once it is in the free space, now once it is in a certain medium of certain mu value and of certain epsilon value, then the value of the intrinsic impedance will change based on the value of the medium parameters. So for any medium, we can define that the value of the intrinsic impedance will be equal to the mu r mu naught divided by epsilon r epsilon naught. Right. So depending on the characteristic of the medium, we have the values of mu r and epsilon r. So these are the relative permittivity and permeability values. So these values we will have. So if we know these values, we can substitute them and find the intrinsic impedance value. Okay. So most of the time we are considering like mediums which are like non-magnetic, or the mu r value is 1. So for non-magnetic medium or materials, the mu r value is 1. So in that case, the value of eta will be the eta naught divided by the square root of epsilon r. So only the value of epsilon r will affect the intrinsic impedance, affect the impedance value. So anyway, the value of the impedance, intrinsic impedance value, should be in terms of omega. Right? So those are the things related to wave impedance. Okay. So I have 2 other parameters that I need to mention about the plane waves. I'm going to erase this. So for the mid-exam, you have to go through these theories and come prepared. Okay, so I will be asking questions regarding these concepts in the mid-exam. So the next thing is, the next property that is of the plane waves is that the cross product of the magnetic field and the electric field and the magnetic field, the cross product will give the direction of the wave propagation. Okay, so that is the property number 4, right? So if I'm going to explain it further, right, if we have components of electric field and magnetic fields in certain directions, the curl of those 2 vectors will give the direction of the wave propagation. So in this case, where we have the direction of the electric field along the along the x-axis direction and along the y-axis direction, let's say, then the z-axis will be in here. So the wave propagation will be along the z-axis. So the wave amplitude will be same if it is a free space. So since we are considering lossless medium, then the amplitude will remain the same and it will be propagating in this direction. Okay, so the direction can be found by taking the right hand rule. So you can keep your fingers along the along the direction where we have the you can keep the fingers of your right hand along the electric field direction and then move it towards the magnetic field direction. Then once you move it, the direction of your thumb, the direction of your thumb will be the direction of the wave propagation, right? So the direction of your fingers will be directed from the starting vector up to the ending vector. So the direction of your fingers will show where the vectors are moving, from which vector to which vector it is the field is moving. Okay, so if you have, for example, the let's say the magnetic field in this direction and let's say the electric field is in this direction, right? What is the direction of the wave propagation? Right. So if you take the fingers starting from the electric field and if we if we move our fingers from the electric field towards the magnetic field direction, our fingers will move in this direction. And then our thumb will be in the vertical direction. In that case, the wave will be propagating in this direction. So the wave will be going in this direction. So if this is a certain axis, so let's say this is the x-axis, this is the y-axis, then the wave will be propagating in the z-axis. Right? So you need to find specifically in what direction the wave is propagating based on the direction of the electric and the magnetic fields, right? So if you are given a question where I'm giving the electric field and the magnetic field, you should be able to draw the direction of the wave propagation by drawing the wave propagating in that particular direction. Okay, so if we have, for example, the electric field in this direction and the magnetic field in this direction, for example, then the fingers will be moving in this direction, but the thumb will be in the vertically downward direction. In this direction, the thumb will be pointing. So therefore, the wave will be propagating in this direction. Okay, so wave propagation will be along in this direction. So that is the idea regarding the wave propagation and how to find the direction of the wave propagation. And then next, I'm going to discuss about the velocity of the wave propagation. Okay, so I'm going to erase this. Okay. Velocity of the wave propagation. Which we call as phase velocity. Right? So phase velocity we call as v phase, for example. Okay, so it is given by the equation displacement over time, right? So we know that velocity is given as the ratio between displacement over time. Right, so this one we can denote as displacement at certain time instance t1 and the time instance t1. So once we try to use the parameters that we already know, we can find the displacement by taking the displacement we can find by taking the multiplication of the angular frequency by the time duration of t1 and divide by the wave number, which is k. Okay, so the wave number, as I said before, is the rate of change of phase. Okay, the rate of change of phase per unit length. Okay, so therefore we have its units as k radians per meters. Okay, so I will explain that further. Okay, so once I have this kind of equation, I can find the displacement using this ratio W omega T1 over K. Using that, I can find the displacement in terms of meters. Then I divide it using the time duration of consideration. And then using that ratio, I can find omega over K ratio, I can find the meters per second velocity of the wave. Right? So I mentioned to you about the K, right? So the K is, I mentioned it was omega square root mu E, right? So there's another equation that defines K. So that is known as 2 pi over lambda. Okay, so this is another equation that is used to define K. So in, this electromagnetism and in physics, we have several definitions for the same parameter. So the wave number is defined using this method and also using this method. So depending on the situation, we use the equation which satisfies us most. So the wave number, as I said before, is the parameter that gives us the rate of change of phase per unit length. Okay, so the amount of phase change per unit length is given by wave number. So how we find it is by taking the ratio between the value of 2π over wavelength. So 2π over wavelength will give us the amount of phase change per unit length. So based on that, we determine actually the frequency of the wave. So K number is essential for us to identify the frequency of the waves because it gives us like how frequently a point in the wave is changing with respect to the wavelength of the wave. Okay, so based on this expression, we can see that this parameter is having the units of radians per meters, right? So the wave number has units of radians per meters. So since I want to find the displacement of the wave along the direction of the wave propagation, I take the ratio between the amount of angle that I moved over a time of t1 divided by the amount of angle that I move per unit distance. So with that, I find the amount of distance that I have traveled in the time duration t1. So with that, I find this as the solution for the wave velocity. Right, so this is the wave velocity equation. Right, so if you are given the values of omega and k, you need to find the velocity value of the wave. Right, so next we are going to learn about the attenuation and why attenuation happens in a wave and how it happens. So that is a new section. So with these 5 properties, I end the discussion about the uniform plane waves. Right, so uniform plane waves, we discussed for a situation where the wave is propagating along a lossless homogeneous medium, right? So in that medium, we were able to say that the amplitude, frequency, velocity parameters were constant, right? Impedance, the intrinsic impedance parameters were constant. So those parameters only we derived in this section, right? So the intrinsic impedance, the velocity, those things were actually constant, and we were deriving those using equations in this part. So next part we will be discussing about the attenuation. Okay, so before moving that, I will try to answer your questions. Omega is the angular frequency. Okay, so actually we can't increase the amplitude along the z axis. I mentioned to you there's no like energy source that will increase the amplitude of electric field while it is moving in the in a space very far from the source. So the lessons that I'm covering for the mid exam, you have asked. Before that, I will go to the next questions. So omega is the angular frequency. Okay, so you know the angular frequency as the angular frequency that we discuss for normal wave propagations, right? So the lessons that I have covered for the mid exam, lessons that I have covered for the mid exam are all the lessons that I have covered so far. Everything that I have covered so far until now will be coming for the mid exam. So in the first, sections, I have discussed about the fundamentals of vector calculus. Those things will not be asked, right? But actually the content that I have covered is used in the other sections. So this thing I will not ask, like what is the curl, what is the grad, those things I won't ask, but I will check the application of those vector calculus in the other sections that I have covered, right? So basically starting from the content that I have started related to electric field, magnetic field, uniform plane waves. Before that I have covered regarding Maxwell's laws. Then uniform plane waves. And then I will cover the content related to transmission lines and antenna theories. But basically up to this point, I will be covering in the mid exam. So you need to register for the mid exam in order to get a paper. I won't provide papers to you if you haven't mentioned your name in the form that I have provided to you. Okay. So another important fact that we are going to discuss is about the attenuation of the waves once it is propagating in the medium, right? So far we have discussed about lossless mediums, but once we have a lossy medium, our wave can get attenuated. So under lossy mediums, our wave can get attenuated. So as the next title, I would say wave propagation under lossy mediums. Okay, so once the wave is propagating under lossy medium, the wave will have an attenuation. The wave will face attenuation. So the amplitude of the wave will decrease over the time. And once we take the time axis like this and the amplitude axis like this, then actually displacement axis in the y-axis, then we can show that the displacement or the amplitude of the wave is decreasing with the time. So we have the wave amplitude decreasing with the time, and it will decrease to a very small value with the time and the distance that it travels. So the attenuation, we try to reduce at to the best of our ability, but we cannot prevent it in the real world scenarios. So attenuation is the reduction in the amplitude and the energy of a wave. The reduction in the amplitude and the energy. The amplitude reducing means energy reduces. The amplitude reduction of a wave as it travels through a medium. Okay, so as it travels through a medium, its amplitude and its energy can get reduced. So there are some factors that affect this attenuation. So that affect this attenuation. There are several factors. So main factors are firstly absorption. Absorption, where we say that the absorption is the energy absorbed by the medium, energy absorbed by the surrounding medium, especially once it is hitting absorption, when the wave is encountering, or when the wave is hitting certain mediums such as water, rock, and so on. Right. So, for example, if we take the communication of telecommunication systems, if we have a base station that is generating the antenna waves, the waves will be traveling all around the base station, and the waves will be hitting the intermediate rocks and water bodies. So we have the wave propagating in all directions, and the wave will hit these these mountains, trees, and once it hit these kind of objects, like kind of solid objects like rocks, trees, water, the amount of amplitude in these waves get reduced. So if we have these kind of interferences, we need to place more base stations in intermediate locations to amplify the wave amplitudes, or else broadcast from that location to the user locations. So if we want to like reach a certain user which is near this rock area or some kind of obstructing area in the environment, sometimes the user might not get enough signal strength because of the absorption of the energy due to the absorption of the, due to these obstacles of absorbing the energy of the wave. So the amount of the received signal is low. Received signal is low once it moves to a place like this. So if it hits a place like this, the amount of received signal strength is low. Okay, so another thing is like we have scattering effect. So the scattering effect is an effect that can occur once the wave hits a certain obstacle, and the parts of the wave is moving in all directions. Right? So it hits a certain obstacle, and it changes its direction. So the wave is hitting a certain object, and then hitting an obstacle, and then changing its direction. So the total, the wave direction is changing. Now, earlier we wanted to send the wave in a certain direction, but now it has hit and it has changed its direction. So the wave is not going in the direction that we intended to send it in. Okay, so the third thing is that the reflection uh, also a factor that can happen, where the wave will hit a certain object and then it will change its direction such that the wave will totally move back into the same medium that it was traveling in. So the wave is going and then wave is going back into the same source of same environment that it was in. So the wave is going like this and it hits a certain wall like thing, and then part of it is again getting reflected back. So part of the wave is getting reflected back into the same medium that it was in. So this is the first medium, this is the second medium, right? So if the wave is hitting this kind of obstacle and going back to its previous medium, the first medium, then the reflection is happening. Okay, so that is basically regarding the reflection, right? So those are some of the factors that can attenuate the wave and reduce its amplitude. So due to these factors, we need to consider these. We need to consider how to improve the amplitude of the wave. So we need to consider these factors once we try to improve the wave amplitude. So we will be considering about the reflection of the waves, especially in the transmission line content. So next, so this is regarding the wave attenuation that we talked. So this topic is regarding wave propagation under lossy medium and basically regarding attenuations. Okay, so we discussed about the attenuation. So now we are going to talk about another topic, which is about another like problem that occurs with this electromagnetic waves, that is the skin effect. The skin effect. So this is another problem that occurs with the electromagnetic waves. So skin effect, right? So the skin effect is occurring once we have current carrying conductors carrying high frequency signals, high frequency current signals. So skin effect happens only in AC circuits, happens only in AC current carrying circuits. So AC circuits only face this problem. Okay, so if we connect a certain cable, if we connect an AC current to a certain cable, right? So this cable, let's say it is a very good conducting cable. Let's say this is a good conducting cable. So I will denote our conductor like this. So okay, so we are considering a case where we send a certain AC current through a conductor. So let's say this is a conductor. This is a good conductor. Right? Let's say there's current that is coming from here, and this current is a AC current. So AC current needs to be conducted across this conducting medium. So the conductor, we are only considering the conductor here, not the outer surface of the conductor. So there could be some outer covering for this conductor. There could be some outer covering for this conductor. We are considering the conducting material only in this part. So we have some cover outside the conductor. So this is the conducting, let's say, wire, right? So conducting wire. So this can be composed of copper, let's say this is copper. You know, this is a good conductor. So once we are sending this AC current, now since the varying current is produced, right, through the AC current. So the current is varying here. So varying current, right? So varying current produces varying magnetic field, right? So varying magnetic field is created around this conducting current. Around this current, varying magnetic field is created, right? So the current is going through this conductor. So basically, once once we consider about the center of this conductor, the amount of eddy currents that are getting generated around this magnetic field is high. So we can consider about the center of the conductor first. So once I consider the center of the conductor, the magnetic field that is generated will be generated like this. And as you know, now magnetic field creates a electric field, right? So magnetic fields create an electric field, right? So so because of the presence of the magnetic field, the eddy currents are created around the loops of the magnetic field. So once these eddy currents are occurring, the eddy currents are cancelling out the actual AC current that is going inside this conductor. Okay, so the eddy currents will be cancelling out the current that is generated inside this cable and transmitted through this cable. The eddy current is a disadvantage to this current conducting process. So eddy currents are forming because of the magnetic field that is generated. So the magnetic field generates these eddy currents around the basically once we take the center of the conductor, around the center of the conductor. So these eddy currents are getting more powerful once the amount of current that we produce, or the frequency of the current that we produce using the alternating current is high. So that means like when we increase the frequency, the amount of eddy current production is also increasing. Once we increase the frequency, the amount of magnetic field variation also increase. And because of the magnetic field variation increase, the amount of eddy current generation also increase. Because of that, the amount of electric current that can be passed through this conductor decreases. The electric current can only be transmitted or transferred only along the edges of the conductor, because the center current has been cancelled out by the eddy current. Okay, so because of this, the conductor will look like a conductor which carries current only on the outer edge of the conductor. So although this is a copper conductor, the copper conductor will only carry current which are transmitted along the edge of the conductor. Okay, so only the current which is transferred along the edge of the conductor will be carried through this conductor. Other currents will be cancelled out. Because of that, a lot of heat is also generated in these cables, and therefore also a lot of energy loss is happening. So once we are transferring high frequency AC currents through power cables, the skin effect makes the current flow only on the edge of the cables. Okay, so because of that, we actually lose a lot of energy, and we do not want to have this skin effect, right? In that case, there is a solution to overcome this. Okay, so in this case, the skin effect is due to the generation of eddy currents that were generated around the magnetic fields. Okay, so I will write it down. So the varying current generates varying magnetic fields. Right? So the magnetic fields generate eddy currents around it. So magnetic fields generate electric field, and due to a consequence, eddy currents are produced, formed around the magnetic fields. So these are the eddy currents that are forming around the magnetic fields. So because of these eddy currents, the eddy currents cancel out the current that is flowing across the central part of the conductor. Cancel out the current flowing along the central part of the conductor. Because of this, we can only transfer current along the edge of the conductor. We can transfer current along only the edge of the along the edge of conductor. So the middle part of the conductor will not be sufficiently used to conduct the current. Right. So this phenomena happens mostly in situations where the frequency of the AC current is high. Right. So this phenomena happens when the frequency of the alternating current is high. So this phenomena happens significantly when the frequency is high. So we can observe that this phenomena is not that significant once the alternating current frequency is of like 60 hertz and so on. However, once it reaches higher amounts of frequency, the amount of cross-section area that we can utilize in the conductor decreases. We have 60 hertz. We have other, high amount of frequency, let's say gigahertz of frequency, let's say 60 gigahertz, then the amount of area that we can carry the current is limited to only the edge of the conductor, which is a considerably low surface area when considering the entire conductor surface area. So we only have the conduction happening in the edge of the conductor, not all over the surface area. So because of that, we are losing a lot of material and resources once we are sending current in this manner. So as a solution, we provide a solution for this by using only very low cross-sectional areas wires, and then using multiple of such wires in the cable, right? So there's a huge reduction of surface area reduction of surface area that we can use to conduct the current once we use a high frequency. Okay, so once we use high frequency, there's a high reduction of surface area used to conduct the current. In here, once we use only 60 hertz, for example, we can use a higher surface area like this along the cable to conduct the current. So, so in order to reduce this effect, we can use multiple wires in the cable, inside the cable, and prevent this phenomena occurring. So apart from that, the skin effect is mathematically denoted by a parameter called skin depth. So the skin depth is defined as the ratio between 2 rho over omega mu. So that equation is used by us to denote the amount of distance that the conductor will take to reduce the current amplitude by 1 over E value. So I will write it down. Skin depth is a parameter that is used to define the value of skin effect. So it is defined as 2 rho over omega mu. So so the value of rho is given as the resistivity of the cable to the current conduction. Omega is the angular frequency. So if we know that if we know the value of the frequency of the AC current, we can plug that frequency into this equation and find the value of omega. And mu is the permeability parameter. So value of permeability. Using these, we can find the skin depth. So the skin depth is defined as the amount of depth or the surface area, amount of length along the conducting cable surface. I mean, if we take the surface of the cable like this, the amount of length that the the cable has to, we need to move along this cross section of the surface area of the conductor, right? If we take the top view of the conductor, if we move from one end to the inner side of the conductor by about by a certain length, the length delta that we move will give us the amount of length that is required to decrease the current value, by the current value, the initial current value by 1 over E. 1 over E. So E value, you know, it is a constant value. So the amount of length that is required to decrease the current value by 1 over E is defined as the skin depth. So as I mentioned earlier, we can solve this issue by adding multiple wires with low cross-sectional areas, along this surface area that we have in our control. So we have some surface area provided to us to conduct the current. So we can utilize that area and we can deploy some small wires to conduct the current. Rather than using one single wire, we can use several conducting wires. We can use several small conducting wires to conduct the current. So in this case, the amount of eddy currents forming is reduced because the cross-section area is reduced, and therefore the possibility of creating high eddy currents is low, and the amount of skin depth is very low in these kind of small wires. So the solution that we can give or we can have for this skin effect will be to use multiple wires with small cross sections as a combination to conduct the current. So we can use multiple wires with small conductors, with small cross-sectional areas. Small cross-sectional area can be used to combine and conduct the current. Are used to conduct the current. So that is the solution for the skin effect. Okay, so with that, I have discussed about the uniform plane wave. Okay, so I will be discussing about the next section. So I will give you a small break of about 10 minutes. So you can join. I want you to join again at about 10:05 or 10:05, and I will continue regarding the next section of this lesson. This is a new section, so I will give you a certain small break, and then I will discuss about that. So E is not the charge of electron, E is the exponential constant. Right, exponential constant is like, like it is given by the value of 2.13 or something. There's a constant, right? There's a constant value that you define for the value of E, right? There's a value that is defined for E, which is the exponential constant. So exponential constant is the value that is defined here. Okay, not the charge of the electron. So you can find the exact value. Currently, I don't have the exact value with me. You can find the exact value for that. So please take like a break of about 10 minutes and please join back at about 10:10. Okay.